From perilous deserts and isolated islands to towering mountain ranges, wherever the unknown lies, humanity follows. So it comes as no surprise we're preparing to land on Mars and establish the first permanent extraterrestrial colony, perhaps even terraforming another planet into a second blue home. But hold on. Before we can claim this promising future, we must first complete Phase 2 of colonization, establishing a semi-permanent outpost to serve as a base for more human settlers. But this will be challenging. Even for an expansionist species like ours, Mars is extreme. At first glance, it seems familiar: polar ice caps, vast valleys, liquid water beneath the surface, and a day slightly longer than Earth's. Our ideal destination. Unfortunately, Mars is actually a cold, radioactive desert with a toxic, unbreathable surface atmosphere. Mars is so inhospitable, you'd almost certainly not want to go there. The pioneers toiling on Mars will lead an extremely stressful life filled with unprecedented and incredibly challenging problems. Yet many people are willing to undertake this work, and we possess the technology to help them succeed. In this video, we'll assume a previous Mars mission established an excellent outpost, stocked with resources and equipment, and that a lunar base already exists as a hub for Mars operations. Our outpost's first major challenge is the scarcity of energy on Mars. Due to its distance from the Sun, solar energy is only 40% of what Earth receives. Yet even this sparse sunlight is often obscured for days by massive dust storms. Solar power alone may prove insufficient, and alternatives like wind power or geothermal energy are also impractical due to the near absence of atmosphere. Simultaneously, the Martian interior is too cold. In the early stages, nuclear power might be the only option. Since Mars lacks readily available radioactive elements, both nuclear fuel and reactors would need to be transported from Earth. If we could successfully install it, it could power a small outpost for the first few years. Unfortunately, if we cannot breathe this energy, would prove largely useless. Mars' atmosphere is only 1% as dense as Earth's, and consists primarily of carbon dioxide. Habitats must therefore be pressurized and filled with artificial gas made from nitrogen and oxygen. This, however, introduces further challenges. Corners and flat walls are structurally weak, so habitats will adopt rounded, smooth shapes to withstand the immense pressure differential between interior and exterior. Airlocks must maintain perfect airtightness and function flawlessly every time. Without a strong magnetosphere or dense atmosphere, half the radiation from space would strike the surface directly. People on the surface would be exposed to radiation 50 times stronger than on Earth. Spending 3 years on Mars would expose them to more radiation than NASA astronauts receive over their entire careers, significantly increasing cancer risk. To prevent this, we could use a thick layer of solid CO to shield our habitat. This CO can be harvested directly from the atmosphere. Covering the dry ice with a meter-thick layer of dust would further enhance protection. Unfortunately, this means almost no windows. From the inside, most living spaces appear as windowless tunnels. From the outside, they resemble burial mounds. Even this setup cannot block all radiation, but the reduction is sufficient to support long-term survival. However, it won't protect anyone venturing outside. Therefore, remote-controlled robots will handle routine surface tasks while our crew remains inside. Another reason to stay indoors is Martian dust. It is finer than Earth's dust, so it can penetrate our machinery's gears or electronics. Simultaneously, due to its extreme dryness, it becomes highly charged with static electricity, clinging to everything like spacesuits. Bringing significant amounts of Martian dust into our habitat is unavoidable, and it will enter our crew's lungs. Worse still, Martian soil is saturated with highly toxic perchlorates. Prolonged exposure could be fatal, yet this challenge remains surmountable. For instance, spacesuits could be engineered to prevent dust from actually entering the base, keeping it outside the habitat. Okay, great. Now that we've addressed energy and air levels providing humans with a safe, isolated environment and protecting them from cancer, we just need to provide food. If we settle near the Martian poles, water can be easily obtained from thick ice layers. Growing food presents a different challenge. Martian soil is alkaline and lacks nitrogen compounds essential for plant growth. Before we can grow anything, we'll need to purify the soil, a difficult and costly process. Then, recycled biological waste can be used to fertilize the soil. All of this takes a long time and consumes significant energy. So, we might employ hydroponic technology to simultaneously raise fish and plants, diversifying the astronauts' diet more varied and palatable. This would provide crucial morale support for our overworked crew. However, none of this addresses a fundamental issue. Mars' surface gravity is only 38% of Earth's. This leads to muscle atrophy, osteoporosis, and cardiovascular problems. While this may be resolved in the future by creating rotating living quarters, but in the early stages, our crew will have to endure low gravity and slow functional decline through extensive exercise. Crew members may need to rotate every few years, confined indoors in a small, windowless space, performing the same daily routines with the same people and minimal contact with the outside world. They'll face many challenges similar to those faced by Antarctic scientists or submarine crews. They'll undergo rigorous psychological screening to ensure they are mentally strong enough to endure years of such existence. Establishing the first true infrastructure on Mars will be an immense undertaking, achievable only by exceptionally resilient individuals. Fortunately, Earth possesses ample such individuals. That is it. A small Mars base will survive for decades, provided it receives continuous supplies from Earth, resources, parts, nuclear fuel, and crew. Unfortunately, Mars and Earth are separated by millions of kilometers. Their orbital cycles create only one narrow travel window every 2 years. Should an emergency arise at the colony, Earth would be unable to provide assistance until the next travel window arrives.